so far we discussed about random variables, joint random variables and how to represent them. Now we will discuss about random vectors and random processes. You recall that a random variable, it maps the sample space, this is suppose sample space, to the real line. Suppose this is the real line. So, sample space, any sample point is mapped into a point on the real line. Now, when we consider joint random variable, we have R2. So, we have R2 and any sample point will be mapped to suppose a point in the plane. Suppose this is another sample point, this will be mapped to another point in the sample real line. Sorry. So, another point will be mapped to the plane R2 plane, a point in the R2 plane. So, that way we know that a random variable maps a sample point to a real line and a joint random variable maps a sample point to a point in the plane or R2. Now, this concept can be easily extended to suppose n random variables are there, and then we can consider that it is a mapping from the sample space to the n dimensional space R n. We will consider now a mapping from S into R n. So, this is the n dimensional random variable, or we will call it a random vector. In an n dimensional random variable x 1, x 2 up to x n maps a sample point to a point in R n. So, that we have already told. These n tuples x 1, x 2 up to x n can be represented by a vector x. So, we can write x, this is the common notation, we write a vector as a column matrix x 1, x 2 up to x n, or we can write x is equal to a row matrix transpose. Define a random vector x, we can find out the cumulative distribution function. The CDF of the random vector x is defined as the joint CDF of x 1, x 2, x n. So, of the random variables, the CDF of the random vector x is defined as the joint CDF of the set of random variables x 1, x 2 up to x n. Thus, we can write, this is the notation, f x of at point x, x is my point, that is equal to x 1, x 2 up to x n. So, this at this point the joint CDF is defined as that is probability that x 1 is less than equal to small x 1, x 2 is less than equal to small x 2, like this x n is less than equal to small x n. So, this probability actually means the probability that probability of the event. What is the event? As such that x 1 s is less than equal to small x 1, x 2 s is less than equal to small x 2, like that x n s is less than equal to small x n. So, this is the event, and probability of this event is known as the joint CDF of this n random variable or the CDF of the random vector x. We can extend the property of the joint CDF of two random variable to the CDF of the random vector f x of x. For example, we can say that suppose if what is the CDF of f x of suppose at point infinity. Infinity means in this case is equal to, that is f x1 x2 up to xn at point infinity infinity etc. So, this is equal to 1. Similarly, this CDF will be a non-decreasing function of all its arguments, and it is right continuous of all its arguments etc. So, that way n dimensional random vector can be characterized by its CDF f x of x. Now, in the case of a random vector, we can also similarly define joint probability mass function, joint probability density function etc. So, the PDF of a random vector, because random vector we are considering as a single variable, that is why we are calling it as a PDF if x is a continuous random vector. That is, what do I mean? That this joint CDF is continuous in each of its arguments, then it can be expressed as this CDF can be expressed as the integral, that is n-fold integral of this non-negative function f x1 x2 up to xn at point u1 u2 up to un. So, this function is known as the joint PDF. Just like we have defined in the case of two dimensional random variable, in the case of n dimensional also we can define the joint density function with the help of this integral. So, the CDF can be expressed as the integral of the joint PDF from minus infinity up to the point consider x1 x2 up to xn. So, that way we can generally define the PDF of a random vector. PDF of a random vector, this quantity we can denote by suppose f x vector of at point small u. Now, suppose this joint PDF is also continuous in its arguments, it is continuous in x1, continuous in x2 etc. Then this PDF of the random vector f x of x can be expressed as the nth order mixed partial derivative del to the power n del x1 del x2 etc. up to del xn of the CDF. So, that way, just like in the case of two dimensional random variable, joint random variables, we define the PDF as the second order mixed partial derivative of two variables. Here it is the nth order mixed partial derivative of n variables. So, that way we define the PDF of a random vector or joint PDF of these n random variables. Now, this PDF also inherits the properties of joint PDF. For example, here we can find out the marginal PDF. Suppose if I am interested to find out the marginal PDF f x1 at point x1, how I will get? It is the n-fold, n minus 1 fold integral. So, now we can write f x1 x2 up to xn suppose, and then at point x1 we are interested x1 u1 u2 suppose u2 up to un. So, we will integrate with respect to this is n fold integral, n minus 1 fold integral. So, with respect to suppose the u2 up to d u n. So, n full integral, if we n minus 1 full integral, if we perform, we will get the PDF, marginal PDF of x 1 at point x 1. So, this is up to infinity, from minus infinity up to infinity. So, that way we can find out the any order joint PDF also. Suppose I want to find out the PDF of f x 1 x 2 at point x 1 x 2, then we have to perform the n minus 2 fold integral of the joint PDF. So, that way this joint PDF completely characterize the random variables under consideration, how they jointly behave or how they individually behave. Similarly, we can say about joint probability mass function, etc. So, these are complete description of the random variables under consideration. We can define independent random variables. Suppose we have a collection of n random variables x 1, x 2 up to x n. They are called mutually independent if and only if the joint PDF is a product of the marginal PDF. Similarly, we can write also joint main definition. We can include the joint CDF f x 1 x 2 up to x n at point x 1 x 2 up to x n. Okay. So, this will be the product of the marginal CDF I is equal to 1 to n f x I at point x I. Similarly, for the discrete random variables, we can define the independence in terms of the probability mass function. Now, this is mutually independent. There is also a concept called pairwise independent, x 1, x 2, etc. They may be pairwise independent, but when they are mutually independent, then they will be independent for any sub collection of these random variables. Suppose x 1 and x 2 will be mutually independent, x 1, x 2 and x 3 will be mutually independent, like that. But if we consider only pairwise independence, then it does not apply mutual independence. For example, if x 1, x 2 up to x n are independent Gaussian random variables, then we can write this joint density as the product of this individual Gaussian. So, that way it is the product of n Gaussian random variables is with respective parameter mean mu I and variance sigma I square. So, we have defined independent random variables. One more important concept is independent and identically distributed random variables. This is abbreviated as IID random variables. The random variables collection is x 1, x 2 up to x n. They are called identically distributed if each random variable has the same marginal distribution function. That is capital F x I, that is the CDF of x 1 at point x is same as CDF of x 2 at point x, like that CDF of x n at point x. This is true for all x. So, what does it mean? That for all these random variables, each random variable has the same marginal CDF. Similarly, we can define the identical distribution in terms of the PDF also. So, each of, if these are continuous random variables, then each of x I will have the same PDF. Now, an important subclass of independent random variables is the independent and identically distributed random variables. So, these random variables are mutually independent and each of xi's has the same marginal distribution function or marginal PDF. So, that way we tell about the IID random variables, independent and identically distributed random variables. We may have a number of random variables which has the same distribution, each of which has the same distribution, and each of the random variable is independent of other random variables in the set. So, that way we can define the IID random variables in the case of continuous random variable, but the same can be extended to discrete random variables. So, we can consider n discrete random variables, they are independent and identically distributed if their joint probability mass function is the product of the individual probability mass function, that is the independence, and each of the random variable has the same PMF at any point x. If we consider each of the random variables will have the same PMF. So, this is the definition of independent and identically distributed random variables. This is a concept which is very important for our further study. So, we define the random variable, joint random variable, then random vector. Now, we will define the random process. A random process maps each sample point to a waveform. So, suppose we have a sample space like this. So, this is a sample point. Now, in the case of random variable, it was mapped to a point on the suppose real line. Now, in the case of random process, the same sample point will be mapped to a waveform, means it will be maybe this type of waveform it will be mapping. So, that way we see that it associates, if I consider this time axis, then at every sample point and every time instant t to a point on R. So, that way we can define, we can say that this random process is a mapping from the sample space to the. So, we can say that a random process is a mapping from the Cartesian product S T. It associates a pair S and T to a point on the real line. So, that it is a mapping from the Cartesian product of sample space and tau. This is the tau, okay. Time, generally that index set is called tau, S cross tau to the real line. So, that way we can consider the mapping. In the case of random variable, it is a mapping from the sample space to the real line, but in the case of random process, it is a mapping from S cross tau. Tau is the some index set which is usually time. So, from S cross t to R. So, we can define a random process now. A random process on the probability space SFP can be defined as an index family of random variable x s t such that S belongs to S, t belongs to tau, where tau is an index set of usually denoting time. That is why it is a random process, is a function of time, but tau need not be time only, it can be space. For example, we can consider an image as a random process, two-dimensional random process. It is defined on suppose that sample space, and then Cartesian product of the sample space on the image plane. Tau need not be only time, it can be a two-dimensional plane. For example, the image plane, for example, an image can be considered as a random process defined on the samples defined on the Cartesian product of sample space and the image plane. So, that way we define the random process. Now, random process we see that it is a mapping from the sample space to a waveform. Now, if we consider a fixed sample point, then suppose t is varying, then x s naught t is a single realization of the random process. So, we can have a single realization of the random process. Suppose this is some s naught. So, it is mapping to some waveform like this. So, this is a single realization of the random process, which usually the observed data. So, we observe one single realization of the random process. Now, when both s and t are varying, we have the random process. Otherwise, suppose at a fixed point s naught and t naught, this is we will get a single value. Suppose if I consider this value, this is a single value of the random process. Though the random process it is a function of both s and t, it is normally denoted by x t only. Just like in the case of random variable, we denote it by x, omitting the argument s. Similarly, here also we omit the argument s. We can define a discrete random process x n on the discrete points of time. We can have generally in that case tau is a subset of the integer. Such a random process is more important for practical application, because normally we get the discrete data. This discrete data can be modeled as discrete random process. So, this is a discrete time random process, this is a continuous time random process. Probability structure of a random process. Now, how to describe a random process? We know that single random variable can be described by CDF, joint random variable can be described by joint CDF. Similarly, we can characterize a random vector by the CDF of the random vector. The same concept can be extended to random process, but in the case of random process, we have a continuum of time, therefore, infinite number of points in the time axis. Characterizing the random process in terms of the joint CDF is difficult. For example, we can consider for any positive integer n, this collection we can consider xt1, xt2, xtn, etc., and they will represent n random variables. Now, we can describe these points, these random variables by the joint CDF like this. This is the joint CDF of n random variable xt1, xt2 up to xtn, and this we have to define for all n, because any point suppose t1, t2, t3, etc., all possible collection we have to consider. And not only that, suppose on the time axis we can take this place t1 here, t2 here, like that, tn somewhere here, but we can keep t1, t2, etc., anywhere on tau. So, that way also another complexity is introduced. So, thus what we see that we have to define the joint CDF for all possible n and for all possible placement of the time points tn. So, that way describing a random process in terms of joint CDF is difficult. Similarly, we can describe the random process xt by the joint PDF. We can also have f xt1, xt2 up to xtn at point x1, x2 up to xn. So, we can have this joint CDF, joint PDF. So, this is also for all n belonging to the set of natural number and for all placement of the time points t n belonging to tau. So, that way we can characterize a random process in terms of joint CDF or joint PDF. Similarly, for the discrete case, we can define the joint PMF also. These are the way we have to describe a random process if we are interested in the probability structure. So, describing the random process in terms of joint probability, joint PDF, joint CDF, etc. is difficult. Therefore, we can define moments just like in the case of random variables, we defined moments and joint moments. Here also we can define some moments, joint moments, etc. so that we can partially characterize the random process. We can define the simplest moment is the mean E of x t, that is the now at instant t, x t is a random variable. So, we can define the average value of x t, that is E of x t. We usually denote it by mu x of t, and it is the mean of the random process at time t. So, now since random process at different instant of time, it is a different random variable. Therefore, mu x t also will be a function of time. Similarly, R x of t1, t2, this is the autocorrelation function at point t1 and t2. This is defined by E of x t1 into x t2. So, this is the autocorrelation function at t1, t2. So, that way we can define the joint moment. Since we can define any number of random variables, we can define nth order correlation. For example, triple correlation R x of t1, t2 up to t3. R x of t1, t2, t3 is defined as expected value E of x t1 into x t2 into x t3. So, this is the triple correlation function at time point t1, t2, t3. So, that way we can continue the definition of other order moments. So, we can also define the auto-covariance function. That is Cx of t1, t2. This is defined as the expected value of x t1 minus mu x of t1 into x t2 minus mu x of t2. That is equal to, again we can use the property of joint moments. We can define it as E of x t1 into x t2 minus mu x t1 into mu x t2, and this is nothing but the autocorrelation function R x of t1 t2 minus mu x t1 into mu x t2. So, that way we can define the autocovariance function. So, autocorrelation function, autocovariance function along with mean, they can describe the random process partially. I will give some examples of random processes. The first example is Gaussian random process, which is one of the most important random processes. The process x t is called Gaussian if for any n belonging to natural number n, and any time points t1, t2 up to tn, the random vector, we define a random vector that is xt1, xt2 up to xtn transpose. This is the random vectors n dimensional is jointly Gaussian. With the joint PDF is now given by, this is the joint PDF, that is equal to e to the power minus half of x minus mu x transpose Cx inverse x minus mu x divided by root over 2 pi to the power n into root over determinant of Cx. Let us define the terms. Now mu x is a vector. This is the expected value of this vector E of x. So mu x is E of x, that is equal to, now component wise I will take the expected value, that is E of xt1, E of xt2 up to E of xn transpose. Now Cx is a matrix, that is the covariance matrix, that is E of x minus mu x transpose, and then we take the expectation. First we have the matrix x minus mu x into x minus mu x transpose, and expectation of each element in this matrix, that will give us the covariance matrix. So here we determine the determinant of the covariance matrix, and here inverse of the covariance matrix. So that way we define the Gaussian random process. Next elementary example, this is an elementary example of a random process, what is known as the Bernoulli random process. We know the Bernoulli random variable, which can take only two values 0 and 1. Suppose xn at any instant n, it takes value 1 with probability p and 0 with probability 1 minus p. Then this is a Bernoulli random variable, and we may also consider that this, suppose Bernoulli random variable, Bernoulli trials are independent. If I independently suppose toss a coin, then if I am interested in one outcome, suppose head, then this I can take as 1 and tail as 0. So that way we can define a Bernoulli random variable, and if I repeat the toss for different time, then we will get the sequence of Bernoulli random variable, or it is called the Bernoulli random process, and in this case actions are independent. Okay. So we may have a discrete random process, which is where each random variable is independent of other random variables. Now in the case of random process, we know that at different instant we have different random variables. They need not be independent in general. In the case of Bernoulli process, they may be independent, but they are generally dependent. We can discuss different type of dependence. We can discuss different types of dependence. For example, independent increment random process. A random process xt is called an independent increment process if for any n, suppose you consider t1 is less than t2, less than t3, etc., up to suppose tn minus 1 is less than tn, then we can define a set of n random variable xt1, x of t2 minus xt1. Suppose xt1 is a random variable, x of t2 is another random variable. Therefore, the increment during time t1 to t2 is xt2 minus xt1. So this is one increment. Then next increment, for example, will be xt3 minus xt2. So this is another increment. Like that, we can consider all the increments. These increments are independent random variable. Then we call this process as an independent increment process. So, the concept of independent increment process is very important. For example, we can consider, later on we will consider two processes. One is Poisson process. So, this is an example, Poisson process. This is an example of independent increment random process. Similarly, we will have another process called Wiener process. So, Poisson process and Wiener process are examples of independent increment processes. So, here increments are independent. We can also consider a concept what is known as the stationary random process. Now, what is stationary? A random process x t is called strict sense stationary. This is strict sense stationary. So, this we abbreviate as SSS. If its probability structure is invariant with time. In terms of joint CDF, we can write the joint CDF of random variable x t 1, x t 2 up to x t n at point, suppose this set of points x 1, x 2 up to x n. And if we consider the joint CDF at another instant of time, that is x of t 1 plus t naught, x of t 2 plus t naught, like that way x of t n plus t naught. Then at the same set of point x 1, x 2, x n, we are considering these two CDF if they are equal for all n belonging to n and for all placement of t0, t0 and tn, then we call this random process is strict sense stationary. So, what does it mean? That joint CDF for any order n is independent of the shift of the time axis. So, you consider whether at t 1, t 2, t n or t 1 plus t naught, t 2 plus t naught up to t n plus t naught. So, this joint probability structure will remain invariant. So, in other words, the joint CDF is invariant with respect to the shift of the time axis. Now, SSS process, as it is seen from here, it is very difficult to analyze a strict sense stationary process, because we have to consider the CDF of all possible order. So, we require a simpler process, and that is wide sense stationary process. In that case, we do not consider the probability structure, we consider only two moments. So, a random process x t is called wide sense stationary process, a wide sense stationary process WSS if E of x t is equal to constant and R x of t 1 t 2, that is the autocorrelation at instant t 1 t 2 is same as if I shift the autocorrelation time axis by some amount h, R x of t 1 plus h, t 2 plus h. This is for all t 1, t 2 and h. If this happen, then we say that for the this random process mean is constant and autocorrelation is independent of the shift of the time axis, then we say that this process is a WSS process, wide sense stationary process. So, if I put h is equal to minus t 1, what we will have is that R x of t 1 t 2, that is equal to R x of, if I put h is equal to minus t 1, this will be R x of 0, then this will be, if I put minus T1, T2 minus T1. So, therefore, we see that in the case of WSS process, this autocorrelation function is a function of the time lag, T2 minus T1. So, if I denote it by some single parameter tau, then tau is equal to T2 minus T1. This autocorrelation function is a function of tau only. And now, we can define therefore autocorrelation function, since it is a function of the lag parameter tau, we can define Rx of tau is equal to E of x of t plus tau into xt. So, it is a function because time difference will be t plus tau minus t. So, that way autocorrelation function for a WSS process, autocorrelation function of a WSS process has certain property. So, it is a function of lag tau only. We can write Rx of 0. What will be Rx of 0? That is equal to E of xt into xt, that is E of x square t. This is the mean square value of the process. Similarly, this autocorrelation function Rx of tau, suppose, is an even function. How? For example, Rx of minus tau, this is equal to E of x of t. If I consider this definition, t minus tau. So, Rx of minus tau is E of x t minus tau into x t, and x of t minus tau and x t are both real. So, therefore, we can write that is equal to E of x t into x of t minus tau, and that is equal to, if I take the difference now, it will be Rx of tau. So, this is Rx of minus tau, that is same as Rx of tau. Therefore, this autocorrelation function is an even function of the lag parameter tau. Now, there are other properties we will not discuss in details, but this autocorrelation function also give a frequency domain representation of the random process. So, how to describe a WSS random process in the frequency domain? You can consult any random process book where it is shown that there is this power spectral density, this is the average power per frequency, and this is the Fourier transform of the autocorrelation function. So, therefore, to analyze a WSS process in the frequency domain, we can take the help of power spectral density, which is the Fourier transform of the autocorrelation function. Let us summarize the lecture. An n-dimensional random variable, so it is x1, x2 up to xn, that is the ordered pair, is denoted by the random vector x, that is we can write it as a row vector transpose. Now, these n random variables can be characterized by the joint CDF that we denote by fx at point small x. So, this is the CDF, and this is actually the CDF of joint CDF of x1, x2 up to xn at point x1, x2 up to xn. So, this is defined by this probability, that x1, capital X1 is less than equal to small x1, capital X2 is less than equal to small x2, like that up to capital Xn is less than equal to small xn. Now, this joint PDF, this is notation is fx of x. So, this joint PDF is defined through the integration. This is n-fold integration, that is joint CDF is the n-fold integration of the joint PDF with respect to its parameters. So, that way we defined the joint CDF, joint PDF, and also we defined the joint PMF for collection of random variable, and random variables are there, they are represented as a vector, and then we got this quantity. Now, this collection of random variable x1, x2 up to xn are called mutually independent if and only if the joint PDF is product of the marginal PDF. So, that way we can define in terms of the joint CDF also, the joint CDF should be the product of the marginal CDFs. Then we discussed about random process. A random process, it is a function of S and T, sample space, it is a sample point, and T is usually it is a time variable. It is a function of two arguments, sample point and T, and it is usually denoted by xt. S is omitted, just like in the case of random variable. So, a random process is an index family of random variables. So, what do I mean by that? At every instant t, it is a random variable. Xt can be described by joint CDF. So, if I consider any n instance of time t1, t2 up to tn, then we can find out the joint CDF. But this we have to find out for all possible n and all possible placement of t1, t2, tn, etc. So, that way describing the random process in terms of joint CDF is very difficult, very complex task. Therefore, we have to find out some simpler description of the random process. That way, we describe the random process in terms of its moments like mean E of xt and autocorrelation function Rx t1 t2. This is nothing but the expectation of x t1 into x t2. So, this mean and autocorrelation are two important parameters of a random process. Next, we define the stationarity. The process xt is strict sense stationary if the joint CDF for any n is invariant with respect to change in the time axis. What does it mean? Suppose if I have the joint CDF at point t1, t2, tn, then if I consider any shifted version of time t1 plus t naught, t2 plus t naught up to tn plus t naught, then also the joint CDF will remain same. So, this is the strict sense stationarity. This we can define in terms of joint CDF, joint PDF, joint PMF, but this is very difficult to analyze because you have to consider it for all n and all the placement of t1, t2, tn. So, that way we consider some simpler form of stationarity. We discussed about white sense stationary process. So, xt is white sense stationarity, xt is white sense stationary WSS if E of xt, that mean is constant, and the autocorrelation Rx t1, t1 plus tau. So, this time lag is tau here, t1, t1 plus tau, and this is a function of time lag only, it does not depend on t1. So, that way if that happens, then the process will be called white sense stationary. Thank you.